So let's continue on and look at mixtures of gases. We all remember the ideal gas law, PV equals nRT. Note we can solve this law for pressure. All you have to do is divide both sides by volume. Pressure equals number of moles of gas times RT over V. What this then means is if you have a mixture of gases, the total pressure of all those gases together is just the sum of the pressures of each individual gas. We call those the partial pressures. So, for example, if you have three gases in a mixture together, the total pressure is the pressure of gas A plus the pressure of gas B plus the pressure of gas C. For example, air is 78% nitrogen gas, 21% oxygen gas, and 1% others. We'll combine all the other gases right in there. But the total, let's just put in nice round numbers, is 1 atmosphere. So if the total pressure is 1 atmosphere and 78% of the air is nitrogen, that means the partial pressure of nitrogen is 0.78 atmospheres. 78% of 1 atmosphere. The partial pressure of oxygen is 0.21 atmospheres. The partial pressure of all the others combined is 0.01 atmospheres. Now, note with a little math here, we have up here, we know that the pressure is the number of moles times RT over V, which means the pressure of gas A is the number of moles of gas A times RT over V. If we were to divide that pressure of A, that partial pressure of A, by the total pressure, note the total pressure is the number of moles total times RT over V. Note, these two gases are in the same container. R is a constant, temperature is the same, volume is the same. These two cancel out, which means the partial pressure of gas A divided by the total pressure is just equal to the number of moles of gas A divided by the number of total moles of gas. And this little term here, Na over N total, is called the mole fraction because it's the fraction of the molecules of A compared to the total number of molecules. And we can put that in this equation here. The partial pressure of A then equals the mole fraction of A times the total pressure. All right, so how can we use that? Well, here's a little problem here. Two parts. Say you have a 1 liter container at 298 Kelvin, and it's a mixture of helium gas at 341 millimeters of mercury and neon gas at 112 millimeters of mercury and argon gas, and we do not know its pressure. However, we know the total pressure is 662 millimeters of mercury. And right now you're saying, oh, this is going to be an easy question. What's going to be the partial pressure of argon? Well, that's part of it. I'm going to spice it up a little bit here. What is the mass of argon gas present? Not the partial pressure of argon, what's the mass of argon gas present? And I had a second question there, what is the mole fraction of argon? Okay, first question, well, the easy part is to get the partial pressure of argon. We know the total pressure is equal to these partial pressures, so our total pressure equals the partial pressure of our neon plus the partial pressure of helium plus partial pressure of argon. Very straightforward math. Tells us the partial pressure of argon is 209 millimeters of mercury. Okay, that's fine, but if we know the partial pressure of argon, how do we get the mass? How do we get the grams of argon? Good news. Anytime you're dealing with gases and you're wondering, how do I do something? Just first go to the ideal gas law. That's the first thing you need to look at. Maybe that will help me. Well, here's our ideal gas law. Note it's PV equals nRT, and I've just converted N, the number of moles, to grams divided by molar mass. So PV equals grams divided by molar mass times RT. And first thing we need to note is this is 209 millimeters of mercury. Ideal gas law, pressure has to be in atmospheres, so we need to convert millimeters of mercury to atmospheres. 209 divided by 760 gives us 0.279 atmospheres for the partial pressure of argon gas. Well, There's our partial pressure of argon gas in atmospheres. We're told it was a 1 liter container. We're after the grams. Here's the molar mass of argon gas from the periodic table. R is a constant, and we were told it's 298 Kelvin. So nope, we've got everything for this question. We've got all the variables for this equation except for grams, and that's what we're after. Plug everything in, do the math. Grams equals 0.449 grams of argon. That's our mass of our argon. And the second part's actually pretty easy. What's the mole fraction of argon? Well, up here we got the pressure of argon at 209 millimeters of mercury. Recall the mole fraction of argon is the number of moles of argon divided by the total number of moles, but it's also the partial pressure of argon divided by the total pressure up here. So the mole fraction, just take the partial pressure of argon divided by the total pressure, and you get 0.316 as the mole fraction of argon. Note, there are no units to mole fraction because millimeters of mercury canceled out. No units to mole fraction. All right. So this leads us to an interesting thing, an interesting problem we have, but we have a nice way to figure it out. When you're in the lab and you're running an experiment and you're collecting a gas, how does one actually collect a gas in the lab? And it turns out the best way to collect a gas in the lab is over water. So if we look in your book has a really good diagram of this. And let's see. So here we have the diagram in the book, 233 of the Tro book. If you're running, here's just running a reaction with zinc and HCl, it gives off H2 gas. Note that H2 gas is lighter, it's less dense than liquid, so if you keep generating it, it'll generate some pressure. It'll push the H2 gas here through this tube. You have this all submerged in water, and you would have filled this beaker or this container that is upside down. You'd have completely filled it with water before turning it upside down. Much easier to do with a test tube than a beaker, I will tell you that. But as the hydrogen gas starts coming up here, it will start displacing this water. And so you can collect the hydrogen gas given off by this reaction in here. It's a very common way to collect gases over water. If you go to organic chemistry, even in the organic 1 lab, we do an experiment where we generate gases and we collect them over water just like this. Okay, the problem is, what is in here? Well, the hydrogen gas is in here, but there's also water vapor. Gaseous water is in there also. The nice thing is, though, there are lots and lots of tables that tell you, okay, based on the temperature of the water, and it will give you the vapor pressure of water. So you don't even have to really worry about measuring this. As long as you know the temperature of this water, these nice tables will give you the actual vapor pressure. All right. So, not too bad. I'm not sure how it's going to work, but in the lab, if you get to the gas laws lab, in the lab, you will do a reaction where you collect hydrogen gas, and you have to make sure you subtract the vapor pressure of the water. Okay. At this point, probably you're thinking, well, this is cool, but if we're running reactions, don't we have to worry about stoichiometry? Yes, of course we have to worry about stoichiometry. So let's look at this now. Recall from, seems like ages ago, stoichiometry problems. If you have a reaction, A goes to B or whatever. If you have the mass of A, you can convert to moles of A. Use stoichiometry to get moles of B, and then use this equation, grams as moles times molar mass, to get the grams of B. Remember the good old days. All right. Well, when you have gases, because you have that ideal gas law, PV equals nRT, you can use that when you have gases to calculate pressure, volume, temperature, even grams. In a reaction, you just have to remember you have to include the stoichiometry, so you're going to have to eventually get the moles of one gas compared to the moles of the other gas. But once you've got the moles to mole ratio with the stoichiometry, then you can use ideal gas law at either end to convert to whatever term you need. For example, let's look right here. Let's say you need 35.7 grams of CH3OH methanol. You want to run this reaction here. CO2 gas plus H2 gas goes to CH3OH gas. Question, this is gas, hydrogen gas. What volume of hydrogen gas is needed? And at first you might be like, well, how do I even do that? How do I know what volume I'm going to need? Well, we will use our plan up here and we say, okay, we're given our temperature, 355 Kelvin, we're given our pressure. I know that I need to, if I want to know how much hydrogen gas, but I was given how much of this I have, I'm going to have to convert this to moles somehow. So I know if I have my grams of CH3OH, I must convert it to moles of CH3OH. Well, that's pretty easy. Moles is grams divided by molar mass. So we can convert that to moles to CH3OH. Our stoichiometry, well, that's just our 2-to-1 ratio there. So that'll get my moles of H2. But how do I get volume? Well, at this point, you should be thinking moles of H2, of a gas, moles of a gas. I need the volume of the gas. Those are both variables in the ideal gas law, where the moles of gas is this M. Volume is what I'm after. Oh, pressure was given. R is a constant, temperature is given. I have everything I need here once I calculate moles of H2 to calculate the volume of H2. So we just plug in and do that. Take our grams of methanol, divide by the molar mass of methanol, we'll get moles of methanol. Stoichiometry, 2-to-1 from our equation, gives us our moles of H2 gas. A nice little trick in here. The pressure was in millimeters of mercury. Recall, with ideal gas law, you have to convert pressure to atmospheres. So I have to convert my 738 millimeters of mercury into atmospheres. Divided by 760, I get 0.971 atmospheres. So there's my pressure in atmospheres. The volume's what I'm after. Here's my moles that I calculated from up here. Here's ideal gas law constant and my 355 Kelvin. Now, what type of person would give this not in Kelvin but in degrees Celsius? I don't know, but be wary of that. Whenever you're working problems, always watch out for units to be given and not the correct units for the equation you need. Instructors really like to make sure you know how to do your unit conversions. Okay, but you plug everything in there, and there we have it. Our volume of H2 gas is 66.9 liters. Note, yeah, check that out. We need 66.9 liters of H2 gas to give us 35.7 grams of methanol if we wanted to run that reaction. Okay. The next topic in the book is the kinetic molecular theory. This sounds impressive. I hate to tell you it's not all that impressive, but it sounds nice. Kinetic molecular theory is just looking at the molecules themselves. How can we explain the gas laws? By looking individually at molecules and their kinetic energy. All right, there are 3 assumptions to kinetic molecular theory. First assumption, the size of the molecules is small compared to their volume. I mean, a gas will occupy a certain volume, but the actual size of the molecules themselves in that volume of gas is very small. For example, if you're looking at argon gas, the volume of the molecules is only 0.01% the volume of the whole gas. All right, another way of saying that, if you blow up a balloon with air, it's mainly empty space in that balloon. The molecules themselves are not occupying that much space. It is just they are smacking off of each other and they are separated from each other in the gas phase. There's a lot of space between the molecules, much more space in between molecules than the actual physical atoms of the molecule taking up that amount of space. All right, so that's the first assumption. Size of the molecules is small compared to the gas volume. Second assumption, The average kinetic energy of the gas is proportional to the temperature in Kelvin. All right, recall from beginning of the semester, kinetic energy, Ke equals 1/2 mv squared. Well, this kinetic energy is proportional to temperature, which means that at a given temperature, not all molecules are moving at the same rate. A heavier molecule, on average, has to have the same kinetic energy as a much lighter molecule, which means at a given temperature, heavier molecules are moving more slowly than lighter molecules on average. Okay, and the last part of kinetic molecular theory are collisions are elastic. When two molecules smack into each other, or when a molecule smacks into the side of the container, there's no loss of energy, and there was no attraction or repulsion. Two molecules are not attracting each other as they're flying around, and they're not repelling each other either. So those are the three assumptions of kinetic molecular theory. Let's look at how they apply to the gas laws. And this is pretty straightforward. All right. Start with Boyle's law here. Recall pressure is proportional to 1 over volume. The smaller the volume means the more collisions you're going to get. The more collisions you get, each collision has a certain amount of kinetic energy associated with it. And that kinetic energy gets turned into pressure because that energy is a force. Pressure is force divided by area. So more collisions means more kinetic, means more force, means larger pressure as you get a smaller volume. Charles' law, volume is proportional to temperature. Yeah, if you have higher temperature, we just found out that that means the kinetic energy of the molecules is higher. Since changing the temperature doesn't change the mass of the molecules, it must change the speed of the molecules. The kinetic energy is higher, so if with a higher kinetic energy, if pressure is constant, you're going to get a larger volume. Avogadro's law just makes so much sense. More molecules equals more collisions. More collisions, more pressure. More pressure would mean if pressure was going to be held constant, if you're trying to add more pressure but can't because we have to hold it constant, it means the volume would get bigger. And Dalton's law of partial pressure. Note at a given temperature, all the average of all the collisions of different gases have the same kinetic energy. Recall, Ke equals 1/2 mv squared. It doesn't matter what the molecule is or what its mass is at a given temperature, since temperature is proportional to kinetic energy. At that given temperature, the average molecules, no matter what their mass, have the same kinetic energy. And therefore they're moving at different speeds, but since it's the same kinetic energy, it doesn't matter what the gas is when we're looking at the pressure, because it's the same kinetic energy. Okay, so now let's go to temperature and velocity. Actually, I'm going to cut it off here because we're going to get a little bit more involved. This video is already 18 minutes, so let's cut it off here and we will continue on with kinetic molecular theory, temperature and velocity.